I'd like to introduce you to the speaker today. Her name is Sascha Roopa. I'm a very fond fan of hers. She's one of the students that went through our university, and she's got an M from our university. And at the moment, we managed to convince her to come work for us full time as well. So she's now part of the Centre for Water Sciences and Management. Sascha, over to you.
Thank you so much, Prof, for the introduction. Yes, so I graduated from the Northwest University and I am now working full-time at the center. I specialize in water chemistry. I have a liking for the subject matter. So I'm going to get into the presentation for today. And today we're going to be looking at Potchefstroom's water yesterday, today, and tomorrow. Okay, so the layout of the talk today is we're going to talk about the history of Potch and its water management and look how the start of gold mining upstream affected the water resources. We're going to look at the results of dewatering and then look at the current situation in the area. Where's the water sourced from? How is it mixed? And then what is the quality of the water in the area as well as the drinking water that we consume. And we will be comparing that to bottled water, which has become popular in recent years. And at the end of the lesson, we're going to look at the future and what would happen if the mines stop dewatering and how will that affect the amount of water that's coming in as well as the quality of the water. Okay, so Mooirivierdorp was established on the west bank of the Mooi River in the neighborhood of Ouderdorp, and that was closer to Boskop Dam, if you know the area. In that area, there was heavy rainfall in 1840 that caused flooding. So the town had to be moved 10 kilometers downstream, and that was when Potchefstroom was established. And when that was established, a canal was built from the river itself that transported water through furrows to the streets to each house. So this is a map of the area. We have Boskop Dam over here. So Ouderdorp, the neighborhood, was on the banks of this dam, and it was established on very thin soil over dolomitic rock, and that's what caused the flooding and the movement of the town further south. The movement was then established in this area, which is on a dolerite sill, so there is less flooding that occurs in comparison to the wetlands in the area further upstream. Then in 1886, there was the discovery of gold in the Highveld, so that was in the Johannesburg area, and that later was moved to the area in the west, which is now known as the West Rand, which is 30 kilometers west of Johannesburg. And in 1899, it was the start of the Anglo-Boer War, which ended 3 years later in 1902. And this is just an image of the Mooi River and the soldiers bathing in the river from 1900. Okay, then in 1900, the area between Potchefstroom and Johannesburg, where the Wonderfontein Spruit, the river, lies, was an area where farming was prominent, and that was due to the abundant supply of dolomitic water from the natural springs that occurred in the area. Then in 1924, Potch Dam was established. It was a very small dam to meet the residents' water needs, and water was purified in the area as well. Then in 1926, the first piped water was received to Potchefstroom, where it was piped to residents. And then in 1930, agriculture and mining coexisted as mining increased in the area. And this increase led to the mine voids being flooded and the need for large capacity pumps to dewater these mine voids. So this is just an image of the mine voids that became flooded, and that was the main reason for dewatering. Okay, then in 1959, there was a need for a more extensive water system because Potch Dam was quite small, and that's when they established Boskop Dam. And water was then transported with canals towards the Mooi River. So Boskop Dam is situated in this area over here, and it's fed by water from the Mooi River that runs over here, as well as the Wonderfonteinspruit, and then a spring that occurs in this area known as the Gerard Minnebron. Then in 1960, the state accepted a proposal from the gold mines to dewater the area, and as a result, the water table was lowered by 100 meters on average. So the dewatering only occurred in areas where the mines were, so where the mine voids were. Adjacent to that, there was no dewatering, so the water still exists in the dolomite. Okay, then this is just a graph of how the water level decreased during dewatering after 1957. And the current state is the water is found at a depth of about 150 meters. Then in 1962, because of the dewatering, a number of sinkholes developed in the area, but a major sinkhole developed in 1962 at a crusher plant at one of the mine shafts. The crusher plant itself sunk into the sinkhole and it killed 29 people. So what happens when sinkholes form? It usually forms in our carbonate rocks. So here we can see our dolomite. And our dolomites consist of carbonates as well as calcium and magnesium. They are very easily eroded chemically. And when you have rainwater that reacts with carbon dioxide in the atmosphere, it forms carbonic acid, which has a pH between 5.5 and 6.5. It dissolves the overlying dolomite that then moves into, not mine voids, into cave systems, and it causes the ceiling of the caves to become weak and to then sink in, causing the sinkhole. So this is the image of the sinkhole that developed. It was 55 meters wide, and the rubble was found 30 meters deep. You can understand that creates issues for recovery of lives lost. Then in 1964, in the area, there was a house that also where a sinkhole developed, and the house also disappeared into the sinkhole, and the 5 people living in that house were killed. That one was much deeper. It was 100 meters deep. So it was very difficult to recover the bodies. I was reading about it. I'm not sure if they had recovered all the bodies in the house. Then in 1970, there was a total of 54 sinkholes that developed in the area. Here's a picture of one of the dolomitic compartments where you can see the sinkholes on the surface. Then, in order to manage the surface water in the Mooi River, in 1971, they established Clark's Kraal Dam in the western and eastern banks, and they cemented that. So that dam is located further north, and that mixes in with water from the Boskop Dam to give us Potch water. Okay, then in 1975, there was another sinkhole that developed below a railway, and a train moving over had to stop to prevent it from falling into the sinkhole. Here's an image of the train above the sinkhole over here. So at night, the passengers had to be evacuated. You can see that this carriage in the center is falling in. Then in 1977, due to the continuation of mining and for it to happen economically and safely, they had to create a 1 diameter pipeline that flows over the dolomitic compartment so that they limited infiltration into the mine working areas. And this is an image of the pipeline. You can see that it's a cement pipe and it's open above. Okay, so the area geologically is made up of 3 formations. The bottommost formation is the Wits supergroup, which is where we find our gold reefs and is the area which is mined. Above that, we have the Ventersdorp supergroup, which is a lava. So it's not very porous. And then we have our dolomitic area, which is made up of dolomite as well as schitt. And above that, in the Transvaal supergroup, we also have a Pretoria group, which is made up of sediment. So we have sandstones in this formation. Okay. The geology is also divided by cyanide dikes from the Bilance group rock formation. You can see them lying across the area itself, and it divides the area into compartments. The main compartments where the mining exists is the Turffontein, Oberholzer, Bank and Venterspost compartment. So what happens is in these compartments is the first one would fill up with water, so it will be recharged, and then it will flow out as a spring at the lowest level and along a dike. And as it flows out, it recharges the next compartment, and your spring will flow out at the lowest point, and so on. So that is how the system works as simply as possible that we can explain it. And the reason for dewatering this area is because all of these compartments were filled, especially in the dolomites, and this flooded into the mine shafts in the mine working areas. So the dewatering need to happen to remove all that water so that mining could happen economically. That was pumped out, and some of the water was used in the mine process, but a great amount was also transported back to the surface water. Then this is just a map of the areas that were dewatered. So we can see Oberholzer, Bank and Venterspost was dewatered, and the compartments adjacent to that remains the same. Then this is just a map of the area. You can see the mines in the gray colored areas, and then we have dots over here that represent the springs. So these 3 here are still flowing, they are colored in, but all of these over here that exist along the dikes have dried up since dewatering. You can also see a cross section that shows the current water level due to dewatering and the water level that existed before the mines pumped water out. Okay, so currently what is happening in the central compartments, the water is removed. Okay, and then this is just a map of the pipeline, the 1-meter pipeline that prevents infiltration into the mine working areas. This is just a water balance. You can see that water is extracted from the surface water system by the mines as well as the wastewater treatment works, and then it is also pumped back into the system. And then in this area, we see that there is maize farming. They do use a little bit of water, but upstream, there is no agriculture because there's no water from the springs that existed previously. Then there's a total of 110 megaliters per day that is lost after the dewatering area, and this we assume fills the dolomitic voids. And then we have water that pops out over here at one of the eyes. The first eye is the Gerard Minnebron eye, and that is a spring. Okay, so we're going to look at some data of the area, chemical data. And these are the sample stations or the monitoring stations. We have the Mooi River over here. It's downstream of Klerkskraal Dam. Then we have the Gerard Minnebron, which is the spring, the Boskop Inlet, as well as the outlet, Potch Dam, and then River 1, which exists along the town of Potchefstroom. And then we also have tap water. It is not on the map, it is off the map, but the tap water is purified just before Potchefstroom, and then it is piped to the reservoirs. So the purification consists of treating the water chemically and then filtering it and then piping it to the reservoirs and then to the rest of the houses in the city. So we looked at different parameters, chemical parameters of the water, and we compared it to the SANS 241, which is the South African national standards for drinking water. And this is the data from 2013 to 2000 and to the end of 2016. We have the pH in this graph. You can see that it follows within the standard range. There's one outlier here for River 1. For some reason, the pH was very low in that year or at the beginning of 2014. We can also see at the same time there was a spike in TDS. But all the other data lies within the national standard range. The same with calcium. Calcium is very high, but it is also in the normal range, and it is very normal for dolomitic type rock. Dolomitic type water. The same for magnesium, because we find calcium and magnesium in our dolomitic waters. Then the sulfate is a bit elevated in areas. You can see here for Potchefstroom, it was elevated in 2013, as well as at the Gerard Minnebron sites over here in 2013 and 2015, but mostly it stays within the national standard range. The same for chloride. And then uranium spikes in the Wonderfontein itself. And that could be due to the mines feeding water back into the Wonderfontein Spruit. In the aluminium, there was no data for the different water systems, but we do have it for tap water, and it's in the normal range. Arsenic spikes in 2013 in the Mooi River, as well as Potchefstroom and the Boskop Inlet, but other than that, it is in the normal range, and you can see that most of the time it is under the detection limit. Then cadmium spikes as well at times, but not in tap water except in this position. But that was just a one-time occurrence. Other than that, it stays below a detection limit. Then chromium, there is a bit of chromium in the water, but it is underneath the national standard range, which is 0.05 milligrams per liter. And then copper is quite low. Fluoride spikes a little bit, but not in tap water. So it's only in River 1 on the banks of the river that's adjacent to the city, as well as in the Wonderfontein Spruit over here. So it's safe in terms of consumption. Then iron is quite low throughout. And then lead also spikes a bit at the end of 2015. Okay, manganese also, we have high manganese concentrations in our soils in South Africa, so we would expect some spikes, but the spikes are only along the city. And then selenium is not something that we need to be worried about. Nitrate as well, it falls within the national standard limit. Then nickel spikes again, and I've seen that nickel corresponds to the lead concentration quite well, so that spikes sometimes above the national standard limit, but it is lower in the tap water. And then the last one is zinc, and zinc is within a good range for all the river sources. Then in 2012, there was a study done at this university, and they looked at the tissue of cows and the tissue of their muscles kidneys and a liver, because you have your heavy metals that accumulate mostly in your liver and your kidneys. And these were cows that were non-pregnant and non-lactating. They also consumed the water of the Wonderfontein Spruit as well as the vegetation. And cows are known to consume a certain amount of soil. So they consume on average about 1 kilogram of soil per day, and that's to feed minerals back into their system. So um, they also use supplements like we do. Okay, so the study looked at cadmium, chromium, and chrome and uranium in the tissue of the cows, as well as the hair and the milk. So from the data, we can see that chrome hyperaccumulates in all the tissue of the cow. It's also found in the grass, and then there's a little amount that we can see in the milk. Then cadmium will hyperaccumulate mostly in the kidneys. We don't see any of that in the milk. And then uranium is found mainly in the liver and the hair, but you can see it's found throughout all the tissues, all the tissue of a cow. And from that results, there was a risk assessment done on an average human with a weight of 70 kilograms. That lifespan lasted 70 years with an exposure to the meat of 50 years. And it was found that cows that graze in the area cannot exceed consumption of 380 grams per day, whereas a control, you could consume 1.8 kilograms of that per day. Okay, then there's also data for that. Then we're going to move on to comparing the water to bottled water. So I just want to define some of the different types of bottled water. We have natural mineral water, which is water that is bottled from a natural source. It is untreated, but it contains trace elements as well as major elements. Then we have natural water, which is derived from underground and underground formation and has not been modified. And then we have spring water, which flows naturally on the surface of the earth, but it's essentially groundwater that is bottled on the surface, either through a spring or tapping from a borehole itself. But all of those three examples are non-modified, whereas prepared water is usually tap water that has been treated. Then these are just the different types of natural water that we find. We are all familiar with Valpre and Nestle, as well as our Woolworths brand. And then we have prepared water. Examples of that are Bonaqua and Oasis. And these water brands undergo a process of reverse osmosis. So we looked at the chemistry on the labels of these brands, and we compared that to the tap water as well as the surface water and groundwater. And when looking at the label information, it was seen that nitrate levels in the natural water brands exceed that of the national water drinking water guidelines. That is an issue because your nitrate will then combine with hemoglobin, and hemoglobin transports oxygen. So then it creates a red blood cell that is incapable of transporting oxygen. And that becomes a problem in infants, especially if they have a vitamin C deficiency. And then from the reverse osmosis brands, there was one dispensing shop that did not comply with label information, but it was well within the drinking water guidelines. Okay, so then this is just a graph where we have the total dissolved solids versus pH. You can see that our reverse osmosis has a very low TDS that is expected, and our natural water that is derived from mostly groundwater in springs is found a little higher on the TDS scale. And then we have our groundwater and surface water within the Potch area. Now, groundwater and surface water correspond to each other as well as the tap water because they're all sourced from the dolomitic springs upstream. Here we can see a Piper diagram. The light blue color represents the tap water. It also corresponds to the groundwater, which is the red dots, as well as the surface water found in purple. The alkalinity is slightly lower than those samples, and it also corresponds to filtered water. And that is because the tap water that we find here goes through a process of filtration. Okay, then when looking at calcium and magnesium, the World Health Organization, they have standards for intake. And if we look at the adults from age 19, the average intake should be between 1,000 and 1,300 milligrams per day. Then for the estimated average requirement for magnesium, it should be within a range between 255 and 340 milligrams per day. So if we look at the average consumption in the different countries in the world, South Africa is over here. For calcium, it lies in the lower range and it is much lower than the adequate intake. And if you compare it to the other countries, it's just slightly higher than Indonesia, but it does fall under the lower range in comparison to other countries. Then for magnesium, it is quite average and it is adequate for the female average requirement, but it is a bit low for the male average requirement in adults. Okay, then if we look at the calcium and magnesium data for our tap water, when the natural bottled water and the reverse osmosis water, we can see that our tap water has the range is not it's not in a bad range. It's perfectly normal, so it is consumable. And only a percentage of that is taken in by the body. Then we can see for our reverse osmosis water systems, which we like to drink, it's a bit low, and we would need to supplement calcium and magnesium if that is the water we consume. Then for the future, there is a debate in the area because it's quite complex and because of the mining that exists. So if we look at these diagrams, we can see that we have an underlying rock, which represents the Witwatersrand supergroup that has been pierced by mine workings. So the dikes in the area have been pierced. So there's two trains of thought of what can happen if the dewatering stops and the mine starts decanting water back into the mine. The first one is that a mega compartment will be created where your water level will rise equally to a level where it will then flow out at the lowest level, so at the spring that's at the lowest level. And then there is another train of thought that says that the water will fill up and it will take on the same dynamic that it did prior to dewatering. And this is just the image again of a map of the area. So the two trains of thought again is it will either rise and spill out at the lowest lying area, which is at the Gerard Minnebron, or it will fill up the different compartments and flow out as springs as it previously did. So there's a number of questions that arise with these theories. The one is, will the mines eventually decant? And if so, what will the quality of the water expected? We know that in the East Rand, there is water that is decanting and the quality of that water is not very good. There is acid mine drainage in those areas. Then another question is, will the mine continue to pump, and will that water be treated instead? Or will the natural water levels be restored to spring flow? And then the last question is, what will the quality of the water be that is decanted and that flows from the springs that exist, that is filling our water system in Potchefstroom? Okay, then I just want to give a special thanks to Clockwork Municipality for making their monitoring data available for us. Thank you. Do you have any questions?
Thank you, Sascha. It was an interesting talk. Has anybody got any questions for Sascha? If you do, just put them in the chat and we'll address them. Any questions? Well, if you think of some, I'll ask a question at the moment. Sascha, you know, we've had quite a lot of rain in these last couple of weeks, and we've had a lot of flooding. And one of the questions that have been raised quite a few times now is, how much does the Wonderfontein actually contribute? Because obviously the rainfall's also coming through the Wonderfontein and it's high up in the catchment. Any suggestions on how we can handle that also to improve the situation, that we don't flood so much? Because I mean, our whole mall flooded the other day with the rain.
Yes, there was a lot of flooding in the town. They closed some of the roads. How would you handle that? According to me, according to the municipality, the flooding happened because they opened the dams completely, and that's what caused the flooding. If the rain water is moving from the Wonderfontein into, and there's overflow into the Gerard Minnebron, as well as into the Mooi River, it does become a problem for us, but I think we should manage that upstream instead of closer to the towns where it affects the flooding, the flood zones. Yes, I think that would be, so they need to monitor rainfall as well as the dam levels in each point where there is a dam.
Thank you. I agree with you there, because that's one of the big issues, is that we've stopped monitoring a lot of the dam levels and water levels right throughout the catchment. And so I think it is something that needs to be addressed. Nobody else wants to ask a question?
Cindy asked a question about the quality of are they monitoring the quality of the water abstracted for dewatering? So the mines do monitor the quality of that. The problem with that is they don't make their data available very readily. So that's the issue with the mines, because there's a lot of confidentiality agreements and they don't release their data. I might have overlooked, but a lot of quality monitoring is surface water, which is diluted by rain. Yes, okay, so they are monitoring mostly surface water, but they do look at the groundwater that enters from the Gerard Minnebron. So that is the groundwater source that the municipality does monitor. I hope that answers your question, Cindy.
Are there no other questions? Then I think we can say thank you to Sascha for giving us this interesting talk, and we hope we're going to see you a lot more presenting on such
Yes, I look forward to it. Thank you for having me.
Thank you. Thank you, Landa and the Groundwater Division, for hosting us today. It's been good to see some of the faces again. Thank you.